Good afternoon, everyone. Myself, Ashwin. So let's start with the motivation of my thesis. So as we all know, the ground surface undergo constant deformation due to natural activities as well as human activities. And it is crucial to monitor these changes in order to avoid any destructive events from happening. And in recent year, INSAR has proven to be one of an efficient tool in monitoring these changes over a large area and also for a longer period of time. So the main idea behind my motivation is to detect these abrupt changes or significant changes. In other words, to find the change points in the time series. So there are various classical approaches that have been developed for change point detection. But the problem with the classical approaches, they can't handle the non-stationarity, and also they can't handle the larger data sets now we have available. So this leads to deep learning models. However, supervised deep learning models require labeled data points, which in real data sets is rarely available. This make me to finalize my topic in self-supervised learning for change point detection. Let's start with the introduction. The first INSAR time series consists of two types of data sets. One is persistent scatterer, and another one is distributed scatterer. These are points that constantly reflect the signal back to the satellite. And the difference between the PS and DS, it's the amount of the amplitude they reflect back. Okay, how does a self-supervised learning works? Because we don't give them any labeled data points, how it learns. So there are few techniques for the self-supervised learning model to learn. One of the technique is called contrastive learning, where the core idea behind contrastive learning is to make the similar pairs closer together, and the negative or the dissimilar pairs far apart in the latent space. There are various loss functions to do that. One of the loss function is called, it's called the triplet loss, which is shown in the figure below. Here, there will be an anchor. For each anchor, there will be one positive and one negative samples. After the learning, the positive sample will come close together to the anchor. The negative pair will go far apart from the anchor. This is the core idea. Okay, let's dive deep into the methodology. First, the time series is fed into a denoising autoencoder. And from this denoising autoencoder removes the major noise from the time series, and this then fed into a batch generation. This batch generation splits the time series into various segments of predefined window size. And each batch is considered as an anchor for which a positive and the negative augmentations is generated. Then these anchor positive and negative samples all then fed into my core deep learning core module, TCN decomposition model, which gives us the embeddings of all the three, positive, negative, and anchor. From these embeddings, we calculate the loss using triplet loss, which is then back propagated to the model to find the in order for the model to learn. Okay, let's have a closer look inside the TCN decomposition model. The main component here is the TCN encoder, which inside it consists of various TCN blocks. So this encoder gives us the latent space. From the latent space, we do the average pooling to get the projection net, which is then used for the training process. Whereas for the testing process, we take the latent space directly and compute a similarity score using cosine similarity measure. And then we use a threshold function to calculate the possible change points. Okay. For the training and validation of the models, I will use two types of data. One is the simulated data using GAN network, and another one is the real data which I downloaded from the Copernicus EGMS website. Okay, let's see the results. First, for the simulation data, in the last plot, we can see the change point, which the black one represents the two change point, and the green one represents the change point from the supervised model, and the red one represents the self-supervised model's prediction. As we can see, the self-supervised model predicted accurately where the change point is, in spite of the fact that we don't give them any labeled data points. And these are the metrics I have attained from the testing of the simulated data. Okay. After testing the temporal analysis, I moved on to test the model on spatio-temporal analysis, because the change point doesn't occur in only one time series. It occurs as a neighborhood. So in order to take a whole neighborhood, I took a study area in Mount Etna in Italy. Here I have considered three different types of data: descending, ascending, and ortho data. The descending and ascending data provides the deformation along the line of sight of the satellite, whereas the ortho data provides the deformation along the vertical directions. So let's see the results. Sorry. Okay. So for the ascending and descending data, the model predicted three change points. And for the ortho data, the model predicted 2 change points. The first change point is from October to December of 2022, and the second one is from April to May of 2023, and the last one is from November to October of 2023. So in order to validate this prediction, I cross-reference the prediction with the Mount Etna's eruption history, and all the 3 change points are coinciding with the Mount Etna's eruption activity, which shows that the model was able to predict the change point in the neighborhood. So this further can be used for all the geophysical investigations. To conclude, I have developed a self-supervised learning, which trained on contrastive learning without the need for any labels. And the framework have achieved good results in both simulated data and also in real data. The model scalability and robustness were tested with different kind of data and different scales of data. And for future research, we can further enhance the architecture of the model by combining multi-sensor data such as GNSS or in situ measurements. And we can also automate the whole pipeline by providing real-time or near real-time results. And we can also use transfer learning approach on this model to investigate various diverse data sets on change point detections. Thank you so much.